So today I'm going to be talking about STARMINE, which is our end-to-end system for mining lunar regolith and then processing that regolith into liquid oxygen for use as rocket propellant. So the mission of Starpath is to make life multiplanetary. And one key enabler for this is the ability to make spacecraft reusable. So instead of throwing them away after one mission to the moon or Mars, we want to be able to reuse them multiple times. But a key challenge here is that right now spacecraft such as SpaceX's Starship or Blue Origin's Blue Moon needs to carry all of its propellant for the return trip to the moon or Mars, and this drastically reduces the amount of payload it can carry on each flight. Each spacecraft needs two components for the propellant. One is the actual fuel, which in the case of Starship is methane, and the other is the oxidizer, which is liquid oxygen. And the oxidizer actually takes up more mass than the fuel itself. At Starpath, our goal is to be able to take lunar regolith and refine it into liquid oxygen, or LOX, to use as the oxidizer. So the idea is that one of these spacecraft can land on the moon, can refuel, and that prevents them from having to carry all their oxidizer for the return trip to the Earth. As a result, they'll be able to launch larger payloads to the moon, and this will reduce the number of flights that will be needed to carry enough mass to build up the infrastructure for permanent human habitation on the moon or Mars. My talk is primarily going to be focused on the moon here, but we've also started looking at applying these technologies to Mars, in which case we'd be focusing more on refining Martian regolith into methane. The STARMINE system has three major components. It has the Rover, which you see over here, which will navigate into permanently shadowed regions inside of craters where icy regolith is likely to be present. And then we'll transport it back to the plant, which is this device over here, which will take that icy regolith, separate the water, and then electrolyze it into hydrogen and oxygen, and then turn the oxygen into liquid oxygen for propellant. And the third part is the tower. The tower is a vertical solar array, which will generate electricity to power both the rover and the plant. And our concept here is to be able to launch the entire payload, all three components, on a Starship, a Falcon 9, or a New Glenn, and then have them landed near the South Pole by a Starship, a Griffin lander, or a Blue Moon lander. Once in the lunar South Pole region, the plant and the tower will be positioned by a lunar terrain vehicle, such as the one being developed by Astrolab called the Flex. And in fact, we're designing our plant and tower payload to the payload spec for the Flex. This is our rover. It has 4 independently steerable wheels that are capable of 3 different drive modes. It's got forward and backwards using Ackerman steering, so similar to the steering on your car, except both the front and the rear wheels turn. Then it's got a sideways strafing movement where it can turn its wheels sideways like this, and then navigate again using Ackerman steering sideways. And then the third mode is a rotate in place mode, which gives it a 0 turning radius and allows it to navigate through cluttered environments like areas on the moon which have large numbers of boulders and smaller craters. In addition to this, it has an active compliance suspension, which will allow it to navigate faster over rugged terrain, and also allow it to adjust the height of the robot's body. There are also 2 arms, although only one of them is installed in this video, which contain these barrel excavators, which are used to actually mine the regolith, collect the icy regolith, and deposit it into the dump truck on top of the rover. And that's used to deposit it at the plant. This allows it to, the suspension allows it to change its height to be able to get over larger obstacles, and also allows it to pitch and roll so it can be easier to navigate over rough terrain. And here you can see it transition into its rotate in place mode, so it can navigate tighter corners. This rover development, oops, that went too far. Backspace. Okay. So, the Rover development project started in 2022, and one thing that Starpath focuses on is rapid iteration. So this is the 8th Rover prototype, Rover 8, competed in NASA's 2023 Break the Ice Challenge, and it won first place. That challenge was focused on endurance, and we demonstrated the rover driving continuously for 15 hours. Rover 9, which is the rover in that video, won second place in the 2024 Break the Ice Challenge. And that was to demonstrate mobility over rough terrain, which was designed to simulate the terrain that NASA expects to find on the moon, and also to demonstrate mining regolith under simulated lunar gravity. So earlier in the video you saw it being suspended by straps which simulated the lower lunar gravity, and then also to demonstrate, for example, navigating over this rocky terrain and being able to climb slopes that were covered with material like regolith, which would reduce the traction of the rover. We currently have developed a 10th rover, Rover 10, which is right now as we speak being tested in TVAC testing at Marshall Space Flight Center. That's thermal and vacuum testing. That's Rover 10, and that's the TVAC chamber at Marshall. It's being tested in hard vacuum at very low temperatures, down to -180°C, to simulate mining in a PSR for up to 12 hours, and then also tested under very high temperature settings, which has heat lamps exposing it to 1400 watts per meter square, to simulate traveling over the lunar surface at noon for up to 12 hours. We're doing this so that we can do integrated testing on its ability to conduct mining, as well as mobility and charging, as well as to test the robustness of various components in the lunar environment, such as our actuators and sensors and avionics. And we're going to use the thermal data here to calibrate our thermal models. Currently, the rover is teleoperated. And my focus on the project is to develop the autonomy system. We're in a stage where we're evaluating different sensors to be used on the rover. We're evaluating various cameras which will be used for both teleoperation and visual odometry. We're also evaluating LiDAR sensors and time-of-flight sensors that will be used for mapping obstacles and also for LiDAR odometry. We're working with Nat Gill over at NASA Goddard on a sensor called the WASP, which is a time-of-flight camera that's designed to be robust to the space environment. And then we're also evaluating a couple off-the-shelf IMUs from VectorNav and MicroStrain, and we're planning to acquire a star tracker from Rocket Lab and use that for absolute orientation on the moon's surface. We also have wheel encoders and odometry, but we expect to have a lot of slip, so we don't want to rely on that too heavily. Finally, the idea is that we can use these sensors to get close enough on a return trip to the plant that we'll be able to detect it using something like a radio beacon direction finder. So that if we get into the neighborhood of the plant, then we can lock in on the plant, navigate to it, and then we also expect to have fiducials on the plant for the precise localization to allow the robot to deposit its regolith payload, as well as to dock with the charger. This is an overview of the autonomy system. At the highest levels, the mission planning will be conducted by humans, determining which areas in the PSRs the robot should navigate to. And this goal will be passed down to the global path planner, which will use a digital elevation map from previous sensing on the moon to plan a global path with high-level waypoints. These waypoints will be passed down to the local path planner, which will combine the digital elevation map data with data from its local sensors, such as the time-of-flight cameras and LiDARs, and use them to build up a map to allow it to plan a trajectory from each waypoint, global waypoint, to the next waypoint, including obstacles that weren't present in the DEMs. We also plan to integrate a SLAM system to allow us to build up a global map based on the robot's exploration of the surface. This local path planner will then pass this trajectory down to the reactive controller, which will try to execute this trajectory, but will also be able to override the trajectory if it detects obstacles that weren't detected in the original map for the plan. And finally, that'll be passed down to the motor control systems. The second element of the STARMINE system is the plant. The plant converts regolith into rocket fuel. It has an auger system which moves the regolith through the plant. It heats the water, turns it into steam, and then it will have an electrolysis system using a proton exchange membrane to separate the hydrogen and the oxygen, and a liquefaction system to turn the oxygen into liquid oxygen for propellant. The production target here is to generate 60 metric tons of LOX per plant per year. And the idea here is that you would have multiple plant rover tower systems, and a system of, say, 15 to 30 of these could refuel up to 10 starships per year, for example. This shows an integration test where we're delivering this icy regolith from the robot to the plant. This icy regolith was this Lunar Highlands regolith simulant that was added, water was added to it, and then it was cooled using liquid nitrogen. Here you're seeing the rover dump this regolith payload into the input bin of the plant. And in this test, this regolith is passed through the auger system in the plant and then heated to separate the water from the regolith. In a full system, it would also be electrolyzed and then liquefied. And the idea here is that in a full system, the plant will take in the regolith over here in this input bin, process it, remove the liquid oxygen, and output the dried regolith on the other bin. And then the robot would pick up that regolith and deposit it somewhere out of the way. And here you can see as the robot is navigating away, the plant is depositing its regolith into the auger system. The thermal images on the left over here shows the heated regolith moving through the plant and being refined to generate the steam that you can see output in the video on the right. The third element of the STARMINE system is the power tower. This power tower consists of this vertical solar array that can deploy and retract these solar array blankets. The idea here is that these will be positioned at the areas to maximize solar exposure near the lunar south pole. It will extend these blankets or these banners in order to collect solar energy, and it also has a 1 degree of freedom around the yaw, so it can track the sunlight during the illuminated periods. Then during the night periods, where it's completely dark, it will retract the solar blankets and then heat them so they can survive the night. We are working with Atomic 6 to develop this deployable composite mast that will be 45 meters tall. But it will launch in this compact roll. That's to get it to fit in within the payload dimensions. And then once it arrives on the moon, it will deploy and extend, and then also deploy the solar banners. We've also started looking at site selection and traverse planning. We're using these publicly available terrain data to identify peaks near the lunar south pole that maximize your exposure to the sun. And for example, this diagram over here shows the expected path of the sun through a typical lunar day. And we're choosing these peaks to maximize their exposure to the sun. And then we're also identifying areas, PSRs, within craters that are likely to contain water. And using an A-star path algorithm that tries to minimize the cost function of distance as well as slope to find a path from the plant to the PSR and from the PSR back to the plant. And you can see it over here, an example of that with an exaggerated 8 times the height differences over there. This is like a 15 kilometer traverse, and we view that as being typical. So finally, our next steps here, we're currently designing the Rover 11, and we're designing the hardware to meet the flight specifications. For Rover 11, we'll be implementing the autonomy system, and then we're going to be testing it out in a desert terrain to determine its performance. For Plan 3, we're going to be developing and integrating the electrolysis system so that we can not only take the regolith and turn it into water, but we can also separate the water into hydrogen and oxygen. And finally, we're going to be demonstrating Tower 2, which will take the deployable composite boom, extend it, and also extend the solar banners. Our goal is to have the entire system ready for flight by 2027. Thank you.